Continue. Last week, last class, uh, we studied GLS, right? Or GLS. And lemma 2, I guess. So lemma 2 is another way, another interpretation of GLS. So basically, it minimize the variance of the weighted estimator subject to the model unbiased constraint. And this is essentially the proof is essentially the proof for the solution to GLS. So so I made I wrote the proof. Minimize omega prime v omega subject to c prime omega equal to c. So then we can use Lagrange multiplier, and then take the partial derivative with respect to omega. But omega is a vector. Okay, so column vector. So then this one becomes this, and originally it has a this is quadratic. V is symmetric, so you can get this one, and this one you can get a transpose, right? Because this is a column vector. Omega is a column vector, so that means this is a row vector. But the derivative should be column vector, right? So that means this row vector should be transposed to become a column vector. So that's why you get this one. And so that basically leads you to have this form. So you now express omega in terms of lambda. And then now you can obtain lambda by plugging to the constraint, right? Constraint. And then so then you can put it this guy to here, right? To here, and obtain the solution. So that is the result. Okay. And then AT estimation, we get so in the AT estimations, this constraint can be so because the C is because this is a C, right? Because we are interested in tau. Tau is mu1 minus mu0. So that means we can this constraint is so that means this is C prime theta, but theta is mu x mu1 mu0, right? So then C is this. And then you can get so that you can actually obtain constraint on the omega, which you can express. So you plug in this guy to here to obtain the GLS estimator. So that means you only so we have a 4 parameter, right? Omega 1, omega 2, omega 3, omega 4, 4 parameter, but you have a 3 constraint. So you have a 1 free parameter, right? So you have a 1 free parameter. So that's omega 1. And then the minimizer, the optimal one, so this is not really so you can call it star. So anyway, the minimum variance, you can view it like this, right? I mean, y minus omega x. So what is the minimize of omega, right? I mean, something like that. So what is this? Well, the minimizer is a covariance minus covariance y x and then variance x inverse. Oops. How can I? Huh, I don't know. Should be able to. Let me. Something's quite strange. Let me see. Can I? Stops here. Okay. Ah, phew. Receive. Ah, no. Sorry. Um, okay. Yeah. So that's why you get this one. Get this one. And then the only thing left is to check this one. So so okay, we can check this. So I guess what is the variance of mu hat x1 minus mu hat x0? That is 1 over n1 sigma plus 1 over n0 sigma xx. So that is n1 n0 over n sigma xx. And then this term, covariance mu1 plus mu0, right? And mu x1, mu x0 is, so mu hat 1 x1 and plus, because this is independent, so this is independent. This is independent. I mean uncorrelated. We explained this before. Let's go back. Here, right? I mean, this is this covariance is 0. So covariance, you had 1 and you had x0 is 0, right? So that same thing here. So this guy is 1 over n1 sigma 1x plus 1 over n0 sigma 0x. So then omega hat, this guy is minus n1 over 1 sigma 1x plus 1 over n0 sigma 0x, and then n over, this is inverse, so n over n1 n0 sigma xx inverse. So that's basically is n over n0 b1 minus n over n1 b0. B1 is a sigma 1 actually prime. So now you can basically, and then this guy, right? Gamma star is mu at 1 minus mu at 0, and then minus n 0 minus n 1 time x at sorry, mu at x1 minus n1 over n0. Oops, no one. 0 time 1 minus 0, right? So what I did was simply, use this one and plug into here. Actually, this is prime, right? Prime. So that we can plug in, and then we obtain. So plug in this result to here to get this one, and then you can see that now one more step, one last step is to check. So let me write it again. Tau hat star is a mu1 hat minus mu0 hat minus b1 prime u hat 1 x1 minus mu hat x0 and n0 minus n1 n minus b0 prime x1 minus mu hat x0 n1 over n. Okay. So so that is, so now let's consider what is the x bar, and this is actually, I don't know. I mean, you can, maybe this is too much algebra. So you basically, this guy is indeed equal to this guy. Same way, you had x0 right? Hmm? minus, I guess. What am I doing? Uh, Something like that, right? Or the zero. Huh? Let me see. And one. Oh, sorry. And one, right? And one. And then is this negative, right? Minus. So this guy is indeed equal to mu hat x zero minus of. Okay. So that means tau is mu hat one regression estimator minus mu hat zero regression estimator. Because we're mu hat one regression estimator is mu hat one minus mu hat x1 minus x bar and p prime p1, right? Mu hat zero regression estimator is mu hat zero minus mu hat x zero minus x bar one prime p zero. A lot of algebra, but at the end of the day, we just show the equivalence, algebraic equivalence. Cannot be different, right? You already know the answer. Know the answer. And what we tried is to show the equivalence in either way, right? Either using the original formulation of GLS formula or using the dual representation. Omega, I mean lemma 2. So that's the idea. Okay. So I plan to even though I'm not going to allow Zoom lecture, I mean participation, I plan to record it so that you guys can watch it later if you have something to catch up later. But I may but next year someone else may teach the same course. So then it's probably better close it the lectures next year. So YouTube, my YouTube recordings will be available only this year. Okay. Okay. So GLS is the conclusion is GLS is useful tool for combining information from several not courses, sources. Okay. Combining information from several sources. We need to figure out the mean. So in order to apply GLS, we need to figure out the mean and variance structure, right? And then there's two ways of implementing the GLS. One is to treat theta as a parameter, and the other is treat omega as a parameter. So it's a kind of dual relationship. The mean structure. So that means here this is a p-dimensional, right? P-dimensional. This is omega is more like n. M is the number of estimators, right? The initial estimators. So we have M estimators. We have a P parameter. So P is the dimension of parameter, dimension of a set parameter of interest. Okay, so we have a right dimension of, so P is the dimension of a parameter theta, and but we have a more information, right? So and you can call it N or M, doesn't really matter. So M should be bigger, greater than P. Then you can have you can achieve some efficiency gain, right? Okay, and then optimization. In terms of optimization, we could solve the problem treating theta as a parameter. That means we solve P equations, essentially P dimensional optimization. While omega is a M dimensional optimization. Okay. And basically the mean structure. So mean structure in the linear model for theta produces a linear constraint in the optimization problem for omega. Okay. So that's about the part one. Okay. And then let me stop recording.